This rather scary collection of motley electronics is something I've cobbled together from cheap components in an attempt to control an extractor fan in an internal bathroom. I'll show you the thing working, and then we'll talk about why I would want to do this, how it was designed, and how I calculated the components. I'm testing this circuit with a 25 watt bulb, but what I will be doing is replacing this 25 watt bulb with a 25 watt extraction fan, which is going to be used to extract the moisture from a bathroom. And then there'll be three modes for the fan. Here is the quiescent mode, which is when the fan is being powered at a low power setting so that it just trickle vents. There's the full power mode where the fan is running full blast, and then when you leave the room and switch off the fan will keep running using a run-on timer for a time period set by this circuit over here, and then it'll fall back to the quiescent mode. So looking at the electronics, there's a one-shot timer which switches on this relay for a given amount of time chosen by this potentiometer here. At the end of the period of time, the relay will switch off. There's another relay, this double pole, double throw relay here, and there's a capacitor, which is what I'm now using to produce a low power setting for the fan, giving rise to the trickle venting that building control now seems to require even when nobody's actually using the room. My initial idea to get a low power source was to use one of these units, which is a voltage regulator. There's a potentiometer which allows you to change the output voltage, and what manages the output voltage is this triac. The trouble with this circuit, as I discovered, is what the triac does is it chops up the incoming AC waveform, and although that reduces the amount of power being fed to the fan wasn't at all happy with a chopped up waveform. I'm not sure what it was doing, but I don't think it was spinning, and it was certainly making some pretty nasty noises, so I had to give up on that idea. And thanks to Big Clive, realised that by putting a simple capacitor in series with the power supply, that was going to be enough to reduce the power to the fan. And how did I come up with the capacitance value? Well, the power of the fan or the light bulb is 25 watts. Power is V times I. Resistance is voltage across the resistor divided by the current. So one can also write that the power dissipated by the resistance is V squared over R. Putting in the voltage, I get the resistance of the bulb is something like 2,300 ohms. I'm just going to choose a capacitor which has something like the same impedance as the resistance as a first attempt. The impedance of a capacitor is 1 divided by 2 pi times the frequency times the capacitance. I want to set that to the same impedance as the resistance, 2,300 ohms. Rearranging this, the capacitance is blah blah blah, which turns out to be 1.3 microfarads. So on the basis of this, I've used a 1 microfarad capacitor just to see what happens. It's interesting to look at the voltage across the capacitor while the fan is in trickle venting mode. And there we are, that's 222 volts. We can then look at the voltage across the bulb, 89 volts AC. Push this stuff to one side. The voltage across the capacitor was 222 volts. The voltage across the lamp was 89 volts. and if you add them together you get 311 volts, which is not equal to the supply voltage of 240 volts AC. So what's going on here? We have to take account of the fact that the voltages and the currents flowing in the circuit are alternating current and are out of phase with each other. And in fact a capacitor is out of phase by 90 degrees to a resistance. So I'm taking the light bulb to be a resistance. So if we make an argon diagram where there's 220 volts at right angles to 89 volts, and do a calculation squaring the 220 and adding on the 89 squared, that comes out to be 240 volts. So that's what's happening there. So here's the concept. We have a fan. We have a source of AC power, and we want to do three different things. There's the switch, which allows the fan to run when you go into the room, switch the switch, and the fan comes on. So that's one circuit. We want a run on timer, so that when the switch is switched off, this run on timer circuit continues to have the fan running for, let's say, a minute. And then we want a low power source, so that when the switch is off, the run on timer has finished its thing, the low power unit continues to run the fan at a lower speed. And the trick is how to get these various connections to work correctly. Well, what I came up with is this. It seems remarkably complicated, but here is the switch to the room. So you come in, you switch the switch, and everything starts, and that's connected to a relay. There's this is the relay switching. There's a one-shot timer, which is the electronic circuit boards we saw in the unit. And then there's another switch here between running fast and running slow. And the way we get the fan to run slow is to put a capacitor in series with the fan. So what happens, here's the live supply. Switch the switch to the room. This is a double pole, double throw relay. So you energize the relay, and these two switches switch from one side to the other. So energizing the relay switches the switch to this side, and essentially the fan is being powered directly from the live mains. When you switch the relay off, both switches jump to the other setting. That fires up the one-shot timer, which controls the relay. When the one-shot timer is fired up by switching this switch here off, this switch jumps from this setting to the other setting, which is the fast speed, and that continues to power the fan for as long as the one-shot timer is running. When the one-shot timer comes to the end of its cycle, it switches off the relay, and this switch jumps to the other setting, which is the slow setting, providing power through this capacitor, meaning that the fan will actually continuously run at a slow speed until such time as you come back into the room and switch this switch on again when the whole thing starts again. For even more gory details and details about the components, see the second video. Thank you.